So, continuing our force on a current carrying wire, what happens when you put a loop of wire in a magnetic field? Well, if we look over here at this diagram right there, side 1, magnetic field's going to the right, so fingers are going that way. Looks like the current's coming straight up, so thumbs there, and so our palm is facing that way, so it's forced up towards the top of the page. Side 2, magnetic field is going that way, so that's my fingers. The thumb this time is going down, and so the palm would be facing this way. So side 1 goes up, side 2 goes down. That produces a torque, which is like a force that causes something to rotate. So the loop turns until its normal is aligned with the magnetic field, so that it's this way, and side 1 is as far up as it can go, and side 2 is as far down as it could go. Then it won't want to turn anymore. So to develop an equation, here's the equation. The torque is the number of loops times the current times the area of the loop times the magnetic field times sine of phi, where phi, this is phi, is the angle between the normal and the magnetic field. Now the normal means perpendicular to. So if I have a loop of wire like that, the normal would be there where it's perpendicular to the surface that the loop of the wire is on. NIA is known as the magnetic moment, which is the biggest part that you can change for the loop of wire to change how much torque it has. More magnetic moment, more torque. An electric motor has many loops of current carrying wire, and the loops are attached to half rings. Right there are the half rings. That means the torque turns the loop until the normal is aligned with the magnetic field. At that point, the contacts are not actually touching and making a current go through anymore. So there's no current there. So then it continues to rotate until the rings connect again, and then it's back like the first picture, where it rotates until it's halfway around, and then it's like the second picture, no more current, so the momentum takes it and makes it continue to turn, and so on. A simple electric motor needs to supply a maximum torque of 10 Newton meters. Uses 0.1 amps of current. The magnetic field in the motor is 0.02 teslas. The coil is a circle with a radius of 2 centimeters. How many turns should be in the coil? Well, our torque is NIAB, sine phi. So that is our torque. This is our current. This, well, that's a radius. But that could be used to find our area. And that's our magnetic field, B. All right, since it's a circle, area is pi r squared. Don't forget to change it to meters instead of centimeters. So we have our torque equals N, which we don't know, IA, so pi r squared, and then our B sine Now, why did I choose 90 degrees? I chose 90 degrees because that would be the maximum torque. We wanted the maximum. Multiply stuff together, divide, and N turns out to be 3.98 times 10 to the 6 turns, or approximately 4 million turns. Well, what do they do in real life? They use very fine wire. They can get lots and lots of turns, and then they actually have many loops at many different angles instead of just one single loop. That's all for today. Have a good day.